In the previous video, we extracted our data from the dorsal fin image edges. Now we can use that data to plug into an AI prediction model. We will make a classification prediction model with our data using supervised learning with our two class labels, shark and dolphin. The data files are linked in the description, but you can actually use any data files as long as they are formatted in the same way, with the features listed in rows like this with commas and the class as the last value. Other than that, you just need to update the label names and this code will work for any data files. First, let's make an array to label our columns and read in our data file. Let's take a quick look at the histograms of our data to understand how useful it is. This will plot all the feature values for each sample and distinguish the two classes with blue and red. Going through our values, we can see that some features have noticeable differences, but it seems they are largely centered on the same value. Ideally, we would see very different trends in the two colors, because that would mean the AI model would have a better chance at predicting the differences. Let's hope that later when we run our neural network, it can extrapolate more helpful values from this data. The first step in building our AI model will be to divide up the samples. I'll use the first 80% for training and the last 20% for testing. Let's do a quick data cleanup by separating it into X and Y arrays, standardizing the data, and oversampling training data to have equal amounts of each class. Alright, now let's try training a quick KNN model before we use TensorFlow. KNN stands for K nearest neighbors, which uses proximity to make predictions about the grouping of an individual data point. This is a very common machine learning algorithm, and basically, when the model tries to predict, it compares the test value with the model's trained value and picks the class with the most nearby data points. After building the model, we will run a classification report which will tell us the precision and recall. Precision and recall are not specific to the KNN algorithm, and we can use these metrics to judge the results of many machine learning algorithms. Looking at our classification report, we see our precision and recall values and our F1 score. F1 score is the harmonic mean of a system's precision and recall, so it is better at giving us an idea of the overall performance of the model. A quick refresh on precision and recall. The model looks at the data and detects how many blue triangles it finds. If there are a lot of blue triangles and we only detect a small amount, we have a low recall but high precision if all of our guesses are correct. And if we detect a bunch, but a lot of our detections are not blue triangles, we have high recall because we detected them all, but lower precision because a lot of our detections are wrong. In relation to our problem, this would mean if there were 6 total sharks and we detected 12 sharks, we would have high recall because we detected all the sharks, but low precision because half of our guesses are wrong. When used alone, these metrics are not particularly useful, which is why we pay more attention to the F1 score, which combines them. We want our accuracy to be at least 70% for a decent model, so being at 50% is not good. We can tweak the KNN parameters by adjusting our K value, which represents how many neighbors need to be considered before making a prediction. So I did go back to the data creating stage and added a few more feature values, including the dorsal fin color, the curve of the right side of the dorsal fin, and the height-width ratio of the fin in an attempt to boost our prediction model's ability. The updates for that code are also available in the repo. So let's try building our KNN model with these extra feature values. So we're getting a little bit better of a model, averaging above 50%, but it's not really that much different, and we want a better score. Using a neural network to build our model may give us the best chance of success. We will use TensorFlow Keras to build our neural network. Neural networks build neurons. Here's a nice graphic I found on how neurons are formed. This is from an article I linked in the description. The neurons take in values adjusted by different weights to create a new output. We can keep adding more layers to continue this process to make more weight combinations of the feature values. This allows the model to be analyzed in more ways, which can help find relationships between the features. When adding layers to your sequential model, there is no single formula on how many layers you should use. The best starting point is to find a model that was successful in a similar problem. Then you can experiment with using less or more layers. The more layers you have, the more parameters. Too many layers can cause overfitting. So you have to play around to get the most accurate predictions with the data you have. The starting point for our model will be based off of one of the model examples found in the free CodeCamp video by Kylie Ying, which uses dense layers with the ReLU and sigmoid activation functions with dropout layers in between. I put a link to that video in the description as well. This is where we can get creative in trying out different parameters when building our model. The epochs, number of nodes, batch size, dropout probability. When playing with your model, you may want to create some nested loops that try out different value combinations for these parameters to see which ones produce the best results and have the least amount of loss. So like I said before, our layers are based on the CodeCamp video layers that were used in a similar classification model. I simplified the model a bit further by removing 2 layers, so our model is a simple 3-layer sequential model with 2 dense layers and 1 dropout layer in between. We will compile it with the binary cross-entropy loss function. The dropout layer helps prevent overfitting by randomly setting some input units to 0 during training. Now we can test our model using the predict function in Keras. We will also print out a classification report with the formatted prediction data and the testing dataset. Our classification report looks like it's giving much better results now. Let me also print out our loss value. This is what we will check when trying out different models to pick the best one, which is the one with the least loss. And here we see the printout of our loss and accuracy. We want higher accuracy and lower loss during training. We used the cross-entropy loss function, which tells us how close is the predicted probability distribution to the true distribution. The true probability distribution is shown by P of x and the model's predicted probability distribution in Q of x. When training, if our model predicts that a shark image is 70% likely to be a shark and 30% likely to be a dolphin, we would have around 35% loss because the true probability should be 100% for shark. And you can see the formula using these probabilities to give us that 35% loss. So as you can see, when you're building an AI model, there are a lot of things you can do to improve it. The data itself is probably the most important piece though, as it's usually said that your model is only as good as the data you train it with. Here are some more ways you can improve your model. This tutorial used the shark and dolphin images from the previous tutorial, where we only got about 100 samples, which is a very small sample size, so more would have been better. Some more features we could extract from the dorsal fin images could be tilt from the center, the color variants, color maps, really whatever you can brainstorm when looking at the images. The other way you can improve your model is by using different training methods. Besides KNN and a neural network, there are many other methods including naive Bayes, logistic regression, SVM, to name a few. We could also have tweaked our model's parameters, like the batch size, the epochs, the model layers, and use different types of activation functions. I also could have changed the threshold parameters when calculating the edges in phase 1. I could have adjusted the number of polynomial coefficients when calculating the curves. It really just comes down to what will give you the best training data for the effort it takes to extract it from the images. So try making your own model and see how well it makes predictions with these machine learning algorithms. Thanks for watching.